Swayam Prabha. Digital India. Educated India.
Not that we are not familiar with these rules, we have seen such rules many times, and now already we have seen a specific set of rules for L1 that was a reconstructed L1, and this is a general thing, that is, these rules are not meant for L1 or anything, these are meant for all types. So, because it wants to reach the higher order, as we have seen. ME stands for meaningful expression. So, rule 1, for each type A, every variable and every non-logical constant of this is non-logical constant of type A is a member of MA. And so, we understand that type A, so ME A consists of entities and individuals and variables that stand for individuals. The next rule is very, very important. The first rule is meant for the basic types, the basic type. So, the first type, that is A. Not, there are two basic types, E and T. We are not we haven't seen T yet. For any type A and B, if alpha belongs to MEAB and beta belongs to MEA, then alpha beta belongs to MEB. This syntactic rule is the real blocker. We have already talked about it. We wanted to block the liar-like sentences. We wanted to block Russell's paradox and many other paradoxical situations. That is why we have introduced this type theory. Now, we shall see how this rule actually helps us block undesired rules and stuff like that. Now, for example, this rule, you take something that belongs to, say, for example, M, which belongs to E to T. If you take M and then if you give it X that belongs to E, then the construction will get the type T. You cannot give, for example, B is also E to T. You cannot give E to T, that is B, to M. This is blocked. This is blocked. So, nothing can take a higher type or as an argument, or its own type as an argument. Something can take only the immediately lower type. So, like this, or for example, you can also think of LXY, which is L is the type E to T. Now, this can take first an E type thing. So, for example, so if I put types, so imagine that there is no X, Y or anything, I just put types to it, and we know that L is a 2 plus predicate. So, we first give it X, which is E. So, together they will give E to T, and that is the type for LX, and the moment Y comes, it is E to T, and then Y is also E. So, E to T to E will make it T, which is the type for LXY. So, this is how the types are constructed, and that is how undesired constructions are blocked. We will see the significance of this later. We just read this rule again. For any types A and B, if alpha belongs to ME, that is meaningful expression AB, and beta to MEA, then alpha beta, that is alpha has taken beta as an argument, that expression then belongs to MEB. we understand how that happens. We have seen examples of that, and also we can see some T type example. For example, this is a T to T type operator, and this is a T type operator. So when they unite, what you get, this construction, that is neg mx, gets the type T. So everywhere type, so this is the general rule that will cover all these levels and all these constructions and everything. Then we go to the rules 3 to 7. If phi and xi are in MET, that is if these are formulas, then so are each of the following: neg phi, and we know this thing, we are pretty familiar, these 5 things: neg phi, phi and xi, phi or xi, if phi then xi, and phi if and only if xi. Now these are quantification rules 8 and 9. What does 8 say? If phi belongs to MET and u is a variable, then all u phi belongs to MET. So the first one. The second one is very similar. You just replace the universal quantifier by the existential quantifier. That's it. And then we go to the next slide, the semantic rules. If alpha is a non-logical constant, I don't know, somehow this is not looking very fine. Anyways, if alpha is a non-logical constant, then the value of alpha with respect to mg is the value f assigns to alpha. We know that there are 2 value assigners, f and g. F assigns values to non-logical constants, and g assigns values to variables. Now 1b, this rule, if alpha is a variable, then the value of alpha with respect to m and g is whatever g assigns to alpha. And then now the second rule, that is if alpha is alpha belongs to MEAB and beta belongs to MEA. We have seen how many cases it covers. It covers an infinite. It covers infinite cases. Then alpha beta, where alpha takes beta as an argument with respect to mg, is the value of alpha as it takes beta as an argument. So so it is the combination of functional combination of alpha and beta. We know what happens with the, so this g should be actually there, but it has come here for there are typing constraints and all that, so it should be mg. Anyways, so if phi and xi are in MET, then the value of neg phi, phi and xi, phi or xi and stuff are as specified in L1. We have seen how these are determined. We are not going to do it again. And then the 8th rule, the quantification rule. If phi belongs to MET and u is a variable, then all u phi with respect to mg is 1, if and only if for all e in dA, dA means the set of entities, the value of phi with respect to mg EU, that is this thing, is 1. So we can check it here itself. So what is it? We are trying to compute the value of all, say all x mx. That is one case of the rule, we are of the concerned rule, not that it is everything. We will talk about it later also. Suppose our phi is mx, suppose our u is x. So then what happens? What is the value of this all x mx? Now the value of this with respect to m and g is 1 if and only if what? If and only if for all value assignments, that is for all values of e, the value of mx, not values of e, all values of x, this for all E, this gives 1. Now, let us check whether that is true. What is M? This is M. So, A, B, C, all 3 things are there. So, there are 3 things, right? J, N and J, D and N. We check each and every one. So, M, J with respect to M, G. So, what is E here? So, sorry, here it will be X, M x with respect to A, it is 1 because A is part of M, and then M x with respect to M G B x, which is once again 1, and M x with respect to M G C x, once again this is 1. Therefore, the value of this is actually 1. So, this is 1 we have checked, but that is not true about B, for example. So, all x B x would give us 0. So, because here with respect to A, so for all value assignments it should be 1, but we can see that B x M G A x gives us 0, because not that all value assignments give us 1, we must say that in this case the value of this will be 0. So, we haven't considered kind of vacuous quantification. We will talk about that. What is it? So, and also this rule, it is pretty similar. The previous one was for all and this is for some, that is the only difference. Now, but also we have vacuous quantification. If we take, instead of x, we can also take V0 E, and because that is how they take it in this framework, but it does not matter, it is just nomenclature. In the case of for example, when 2 things are different, for example, there is nothing that stops us for having a construction like all x m y. What will be its value? This is actually vacuous quantification. Why is it vacuous? It is because nothing, so the checking happens with respect to x, because there is no x in this phi, because there is no x in phi, there is no question of having 1. So, therefore, it will always be kind of 0. So, so that is the reason, it will not be 1, right. So, because it is vacuously quantified. So, vacuous quantification does not give 1. So, we would consider this sort of nonsensical, but we need this syntactic structure is all the time there. So, because nothing will, so what value will come out of it? You just give m y and you just give it m and g a x. What will happen? There would be no value here, there is no checking, right. So, how could it be 1? So, by no means it could be 1. So, it is 0 all the time, right. So, yeah, that is one very important thing. Now, another thing, very important thing, we blocked self reference. How? Now, this is how this construction is banned. Because this is banned, now we remember Russell's paradox. The question was whether the set R belongs to itself, and it is the same thing. For example, when we talk about M j, we sort of say that J is a member of the set M. So, here this question does not arise, because J belongs to E and M belongs to E to T. That is why the question whether E belongs to whether J belongs to M arises, and then we can check whether the belongingness is there or not. But in this case it is not possible. It is because this construction is not allowed. They are the same type. Suppose the type of this is A and this is A. So, this construction is kind of banned. That is the reason Russell's paradox is blocked. We are doing lambda calculus. we are actually doing lambda version of semantics, which is called, the language is called L lambda, and we have already seen the basic things. Now we shall see some applications of L lambda and what it can do and stuff like that. So already we started in the previous session, we showed the type theoretic versions of a few things. We defined a few linguistic elements by using the theory of types, that is by using L type. Now we shall see the lambda versions of those things. So we start with non. It is slightly trickier than the type theoretic version of it, but we will see we shall see each and every step, and we will try to understand how actually it works. So non means, for example, as we say, non-violent. We have seen that yesterday. So it is that non. We are going to define non. Now look here, we have two different variables here. One is x and one is v0 e to t, and our intention is to finally come up with the definition of only this part, and other things should go. So this is what we are trying to do. So let us just see the agenda. What is it we should be doing? Now roughly we can see that this part will be the sort of the definition part, and this part will be the definition part. But how lambda operators help us define something is something we will see now. First, let us read whatever is there. For convenience, we are reading it as v. So yes, we assume that, not assume, we can see that it is an e to t type variable, that is, it ranges over say it ranges over m or b. These are our known predicates, and they could be interpreted as we said, man and bald. So anything. So it is, they are e to t type. Okay. So what is it saying? This is saying that for every x that belongs to me1, me, I'm sorry, that is individual type, and for every variable that belongs to the e to t type, that is one place predicate, non that predicate and x is equivalent to, it is not the case that predicate and x. An example of this, for example, when we say that Mohan is non-violent, what is it we are saying? We are saying here it is not true that Mohan is violent. Now they are not identical. Why are not they identical? Because they are different things, yes, but they are equivalent. What does it mean? If one is true, the other one has to be true, and if one is false, the other one has to be false. They are equivalent, they are identical because they are structurally different. So, but also they are equivalent. Now Mohan is non-violent if we translate this. So this is a specific case. How do we translate? Non and violent, a big V, that is a capital V. So non and violent, and then so first non takes violent, that makes it non-violent, and then we give it Mohan. So finally this should, if this is true that Mohan is non-violent, so this will be 1, right. So this means that it is not true that violent Mohan is 1. It is not true that violent Mohan or not violent Mohan is true, right. So they are equivalent. just that we have written. This is the general form of that. This is a specific form, and that's a general form. Like this form is a general form for all x and all 1 plus predicates, whatever they are, known that predicate x is equivalent to this thing. It is not the case that that predicate applies to that variable, to that individual variable. So this is the first step. This is something we need to understand. We need to know that these are equivalent expressions. With this knowledge, we go to the next slide. We also know that this, which means roughly it means that as we say that lambda alpha p alpha is nothing but it is p. We have seen that in the previous session that they are the same thing. So we define whatever remains, all these things will finally go or disappear. What remains is p. Basically we are defining p by this lambda expression. So we know that this thing, you can see that it is the same variable. So basically you are defining this part. We know this. Now what we do is we just we also know that we just add lambda expressions to both formulas, and then what happens? Now this, they are equivalent. They are not equivalent, they are identical. Of course, any two things that are identical are also equivalent, but this is a case of identity. Why so? Because these two are essentially the same thing. Both are lambda expressions, right? Both are lambda expressions, and they are identical, right? So what we did, everything is the same. We just added lambda expressions to both sides. If we just see the previous slide, we just added a lambda here and we added a lambda here. That's it. That much we did. But by adding lambda, we also come up with these identical statements, because as we see that both are lambda expressions, so they are the same thing. And these are not identical because this is one type of sentence and this is a sentence of another type. That is the reason they are not identical, although equivalent. I wanted to say this, otherwise it is difficult to understand the relationship between that page and this page. Anyways, now we know that lambda x non v x is the function lambda x neg v x. We just added lambda, and that is true about all v, that is all 1 plus predicates. This is what we have written here on this page. We go to the next slide. For every 1 plus predicate, it is true that non this thing is lambda. That means that now adding a lambda expression to both sides of the equation, we get. And so we have already, so we just explaining it, whatever we have written here. So we are just elaborating this here. See, for every 1 plus predicate v0 e to t, it is true that this. Now adding a lambda expression to both sides of the equation, we get. Now we once again add lambda. I will try to explain why we are adding so many lambdas. There is an agenda. That is why we are doing this. We once again add these two lambdas, and then finally we are here. This was already there. So you see, this was already there. Now just we are adding two more, just adding lambdas to both the sides, because they are identical. We can do that. It's something like when we know that 5 is 3 plus 2, we can just add, we can multiply 4 to it, to both sides. They will be the same thing. Similarly, we are just adding lambda to both identical expressions, and we get this. And then finally, once again we use the equation this, that is which means basically as we said that whenever we have lambda x p x, we can write that this is nothing but p. So that thing we are doing. So we get back to it. So you get this lambda v0 whatever and x. and here you have lambda x non this thing, right. So because this thing, this variable and this variable are the same, they will go, basically this is defining non, because they will disappear because they are the same variable. So what remains is non. We are just doing that here. So non now is defined as this lambda expression, this lambda expression. So so that's it. So why did we do all these things? We needed, if we go to the first page or the second page is better. Now from this much we know, we just need to add lambdas to both sides until, so there are two variables, right, with non. So two lambdas will actually help both these go. Because there are two variables, we just add two lambdas. So what is the result? Finally, if we just look at it, what remains is, you take the equivalent expression from the first slide, that is just this. Now you just add, what is the final thing? You just add two lambdas to it. First you add lambda x, then you add lambda v0 e to t, that is and then this remains the same. This is exactly what is happening in our case, and the rest will be the same. We can see that just two lambdas are added. What is the moral of this story? The moral is, when something we are going to define, say for example alpha, and the definition is beta. Suppose beta contains n number of variables. It has x1 through xn. The moral is, we have to add lambdas to both expressions. When we are done with everything, we will find that it will be lambda x1 through lambda xn beta. So this will be equivalent, or this will be identical actually to alpha. That is the reason we kept adding lambdas. We can understand the operation very easily. So but this is what we collect, from the whole story. So now by using the same thing, we revisit our object deletion function. That is what it is. We remember that R0 was the function which converts a 2 plus predicate such as eats to a 1 plus predicate. Thus Mohan eats would be true provided Mohan eats something. So this eats 1, or this e to t function has been converted to an e to t function. This is what R0 does. Now once again, how do we understand this? It's now very easy. So this will be the function. How? We are not elaborating on each and every step. From the definition we know that for all v, that is v0 e to t, which means that we are talking about all 2 plus predicates, and for all x, this thing means, so this is the condition, right, the defining condition. What we do, we just add lambdas with all variables, with all the free variables. Now you see, y is not free, y is bound, right. So there are two free variables here. We consider, because the left hand side is being defined, that is not our problem. The defining expression is here. This is the defining expression, and here we find 1 and 2 free variables. We just add two lambdas with it. What we get is this. So lambda v0 e to t, lambda x, then this thing, right. What does it mean? Now we understand the principle that if we look at the defining expression, if there are n number of free variables, bound variables are anyway helpless, because what will you do with the bound variables? Lambda expressions can't operate on bound variables anyway. They operate only on free variables, because lambda expressions, so the lambda operator itself is a binder. It itself is a thing that binds. So so that's why. Now what is it we are saying? We are saying that for all 2 plus predicate and for all x, R, that means we are not just talking about eats, we are talking about eats, loves, sees and everything. So if this is the case, then it is the case that, so basically they're equivalent, there is some y such that v0 e2 e2 t is true of y and x both. That means as we said, we compare these two eats. This is eats 1, which is the 2 plus predicate, y is say the thing, the object it eats. There is something, somebody, so Mohan, so x will be compared. This is for our convenience. There is something Mohan eats. Only in that case can we say that Mohan eats 2, which is the 1 plus predicate. So we can see how this lambda expression works. We just add nothing more than that. We take the RHS and we count the variables, free variables 1, free variable 2, and we just add 2 lambda expressions. And similarly, we could do the same thing with the, for example, the subject deletion function. If we remember, that was RS, and RS takes any v0 e2 e2 t. For example, Rama loves Sita, which is Sita is loved, and x. What then? This is this subject deletion function. It works this way. So it means that there exists something v0 e2 e2 t, and first is so what is it? We are converting Rama loves Rama Sita. We are just converting this to Sita is loved, ls, right? This is the so the conversion is from this L to this L. So the sentences are Rama loves Sita and Sita is loved. These are 2 sentences. So now the point is, this is true if there is something, there is somebody to love x, because here you remember, here x is being there is somebody, yes, here x is the thing, here x is the object and y the subject. The object in the active voice becomes passive voice. So what will be the equivalent expression for this function, for the other one, that is the subject deletion function? It will be lambda y, lambda x, so x is free, lambda v0 e2 e2 t, then comes the expression, which is precisely there is some y such that v0 e2 e2 t x y. There is some y who holds that relation with x. So this will be the lambda expression for R. Sometimes the pen doesn't work. RS, right? So we know now how to define. It is very easy for us. Similarly, we see what to do with something like all and some. We need not read all these things. We just can very easily derive it. For example, how to translate all students walk? We just write for all x, if x is a student, then x walks. So basically, to generalize it, what we do is we just write for all x, this is v0, this will be, so if we write it, so the variable for this will be v0 e to t x implies, this is another, right, v1 e to t x. Now, what we do is, so once again there are two free variables. What all we do is we just add. So here it is 1 2, I have taken 0 and 1, it's the same thing. So this will be a general expression for this thing, that is, if v0 e to t applies to x, then v1 e to t applies to x, kind of a thing. So this, if this stands for, say, s here, not that it stands for s, it is like we are comparing these two things, and this is this thing. So this is a general form, we just add lambdas to this, e to t and lambda v1 e to t. By doing that, what is it, what we are left with? We are left with just the idea, because this predicate is gone, this predicate is gone, and now it is just the idea, and this is bound, x is bound, so we can't do. So this will be the meaning of all, right, because student is gone and walk is gone, so this is just all. And also we can do it partially. For example, suppose we have we want to just say, for example, we want to define, so as I said, a lambda operator is actually a function splitter. So not that all the time we have to define all. If we want, we can also define, for example, all students. How to do that? So we do that in a step by step manner. Yeah, so for all x, if x is an s, then ws. All we can do is we want to keep this part, all students. So we keep this and we put a variable instead of this, v0, because walk is e to t, so v0 e to t x. And then we add a lambda, lambda v0 e to t. Now this and this will go, what remains is all and students, right. So this is how we can split something and define. So all students, we can define all, we can define all students. Also we can define some, and we can define some students. How to define some? And a sum expression would be something like a sum expression, for example, some student walks. It will be for some x, sx and wx. Once again, first we define some students, and then we define in a step by step manner, and then we define some. So it will just be, we keep x because x is bound, some x, that is student x, sorry, sx student x, and v0 e to t x, right. And all we do is we add this lambda expression with this v0 e to t. If we do that, we have defined some student, then nothing, then something will come in, because it's a lambda expression, it's a function, and also it's an e to t function, right, because it can take no, it is not an e to t function, it is an e to t function, because it takes an e to t type and it yields a t type, right, it's e to t. So and third step, we also put a variable in the place of s, that makes it v1 e to t x and v0 e to t x, and then we add these two, v1 e to t lambda v0 e to t. This defines just sum, because student is also gone, right, student is also gone out. Here the constant student is there, here there is no, absolutely no constant except sum remains here. So then this must be the definition of sum. So now we can see what lambda expressions can do. As we said, we will see the power of lambda expressions in many different ways. For example, with very basic ideas, absolutely basic ideas, we can come up with complicated definitions. For example, what are basic concepts? Very simple mathematics. DAB, A uniformly divides B. What is uniform division? For example, we can say that 2 uniformly divides 8, but 2 does not uniformly define 9 because 1 is a remainder. So, uniform division means there is no remainder. So, when we say that DAB, we mean that A uniformly divides B, and then this is plain and simple identity. A is identical to B, that is A is B, and then we have sum. The sum of A and B is SAB, and we have a few constants. We have 2 which is T, we have 1 which is U, and we have 0 which is null N, and we have variables like x, y, z. These are all E type variables, that is individual variables. They range over whole numbers. Whole numbers means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 through n. These are all whole numbers. So, then we will first define an even number. How to define? We know that some number is even only if 2 uniformly defines it, right. So, we remember that we take just the RHS of it. So, this part, and we count the free variables there. We have one free variable. This is a constant. T is not a variable. T means 2. So, we just add lambda x to it. We get lambda x dtx, and then slightly more complex expression, that is prime number. Some people say that 1 is a prime number. Some people say that 1 is not a prime number. Why is 1 a prime number? According to some, it is because if this is the definition, then 1 is a prime number. What is it? X is a prime number, that is p x, if and only if for all y, of course x, y, everything range over whole numbers, for all y, if y divides x, y uniformly divides x, then y is either u means 1, or y is x itself, right. So, all prime numbers are like that. If anything divides a prime number, it is either 1 or that very number. So, now by this definition 1 is a prime number, but then there is another requirement according to some. What is that? They say that you need to have exactly 2 dividers for a prime number. So, in the case of 1, you do not have exactly 2 dividers. The 2 dividers happen to be the same, that is 1, right. So, that is the reason 1 is not a prime number. But anyways, we start with this. Suppose we want to include 1. In that case, this is our definition. So, how many free variables are there? We have y is bound, x is free. So, u is a constant, and x is free, y is bound once again. So, we have just one free variable. So, we add this lambda expression, and then this defines the prime number. Now, we want to exclude 1. How do we do that? We just very simply do this thing, some y d y x implies y is u or y is x, and for all y, and we want to say that x is not 1. And this is and the condition for all y. We are just saying that x is not 1. Yes. So, if any number divides x, then it is either 1 or x, and x is not 1. So, then we can we sort of define, we can exclude this thing, or we can instead of adding it here, we can also do it some other way. We can just write that was whatever we did, and x is not 1. Yes. So, this somehow defines a prime number. Now, slightly more complicated, we define between. As far as the number line is concerned, how to define between? Now, this will have many variables. We tried our journey, we started our journey with a very simple example, then we sort of took up more and more complex cases. Now, as far as this is concerned, we see that y is between x and z. What does it mean? We do not have, look at our ideas, basic ideas. Our idea, we have just these things, nothing more than that. We have to express between in terms of whatever we have got here. So, among these, this is very important, SAB, how to define between. Now, for example, let us look at the number line, and for example, 5 is between 3 and 8, right? Compare x, y, z. Doesn't it mean that there must be a number r such that y, that is 5, is the sum of x and r? X is the first number. So, x is the first number. So, you can see that 5 is 3 plus 2, right? And we also make sure that this number r, whatever is between 3 and 5, the difference between 3 and 5 is not 0, because if it is 0, then the betweenness will go. So, has the difference been 0, it would be 5, and 5 is not between 5 and 8, right? So, it has to be a non-zero number. So, we are making sure that there is some number r such that y is the sum of x and r is not n means 0, r is not 0. And then look at this, z is actually y plus something, something if I write, right. This expression we just see, and there exists an s such that z is the sum of y and s. This is the last number, and that difference, the difference between z and y, is once again not 0. This also has to be a non-zero number, right. So, then we have defined between. But this is not the end of the story. This is fine, but we will see how potent this system is. Now, suppose we want to define something. We want to define between 5, as we said, between 3 and 5. What we do? Suppose 3 is, I do not know, let us give a constant to 3 and 8. So, suppose 3 is the constant E and 8 is the constant G. These are constants, remember. What we do is we just take this. So, what is it? We are saying that there is something x or y between E and G. We are just defining this. What does it mean? It means that there is some number such that in this case y is the number we are defining being between E and G, that is being between 3 and 8. How are we defining? See, we are splitting the function. We are saying that S XR, so E R, and we know that this R cannot be 0. And there exists another number such that the last one, that is 8. 8 is G for us. G is sum of y and s, and now can you see that if we add lambda expressions to it, how many free variables are there? There is just one free variable in the entire expression. Don't look at this part. We have to look just at the RHS. And now you see that this is bound, this is bound, and this is a constant, this is bound once again, and this also is a constant, and this is free, y is free, but this s is also bound. So, and this is a constant, n is a constant, everything else is either a constant or a bound variable. The only free variable you find here is y. So, you just add lambda y. The moment you do that, you define numbers, all numbers between 3 and 8. Look at the beauty of the lambda expression. We have split the betweenness. We have split the fact of being between, and we have created, so we can cook up the definition of between. Also we can cook up the definition of being between 3 and 8. Also we can cook up the definition of having the upper limit as 8. For example, suppose we give it y, x, and we just write g means 8. This says that we are defining, so there are two free variables here, y and x. We are now defining y's being between x and 8, right. So there would be two lambda expressions before this thing, whatever comes in the RHS, and then so we once again we are splitting. So we can have many different things now, and we can define whatever we want to define, and the order doesn't matter because lambdas, so lambda x, lambda y, phi is the same as lambda y, lambda x, sorry, not phi, alpha, lambda x, lambda y, lambda x alpha. So the order doesn't matter. Now after we are done with this, I just want to talk about one last thing, that is, nothing stops us from combining lambda x my. The question is, what is the value of this expression lambda x my? What will be its type and all that stuff? It seems to be an e to t type thing, operation, but does it have, can it be 1 at all? My point is, it will never be 1. Why? The condition, once again I just get back to the definition side so that it makes proper sense. If now look at this, if phi belongs to MET and u belongs to var e, then lambda u phi belongs to me e to t, that's fine. But the point is, this is not saying that phi must contain at least one occurrence of u. So there is no constraint like that. In that case, what is the value of this thing, lambda u phi? It will be a function h from a into 1 0. From a means it will be e to t type, because all elements of a are e type, e to t type, such that for all individuals in a, h e equals 1 if and only if the rest whatever. Now we will see some kind of vacuous quantification here also. Now what is the meaning of lambda, what is the meaning of lambda x m y? It is the function h, but what does the function do? It is, yes, it looks like a function, but it will never yield 1 by taking e, because it will not take anything, right? So there is no chance that it would ever yield 1. That is why always h e will be 0. So this is and you see h is 0 otherwise. So the value of this function is h, which takes e and always gives 0 in case of vacuous quantification. As I said, lambda 2 is a binder, is a quantifier, and it creates this situation. So although this is not syntactically banned, it is useless. Thank you.